Hey guys, this is the third video in my AP Physics 1 review series, and in this video we're going to explore dynamics. So dynamics is the topic that studies motion of objects and the forces that cause those motion. To start off, let's review Newton's first law of motion. Objects at rest stay at rest, and objects in motion maintain a constant velocity unless acted upon by a net external force. And when an object maintains a constant velocity, it's maintaining a constant speed and direction. If there was no force acted upon something, it would not move. And if there is no force acting upon an object that's moving, it would not be affected in the sense that it would not be accelerated. It would continue to move in a constant velocity. So let's say this marker it's at rest right now. The forces are in equilibrium. There's no force. There's no net force in a specific direction. So the pen is not going to the right, to the left, up or down. So it's just at rest. But if this was moving at a constant velocity and there was no net external forces, the forces in all direction were equal, the pen would continue to go in the direction it was initially going at the same speed. That's basically all the first law is talking about. Now Newton's second law is net force equals mass times acceleration. On the AP Physics formula sheet, it's actually written as acceleration equals sigma f over m. And note that these arrows just indicate that it's a vector. Acceleration is a vector, force is a vector. Force is a vector because it's the product of mass times acceleration, and acceleration is a vector. So force is also a vector. This entire line would be found on the AP exam's formula sheet, and I'll link the exam formula sheet in the description below so you can see what the formula sheet looks like. So this and this is exactly the same thing, only the variables are rearranged. Now let's look at Newton's third law of motion. For every action there is an equal and opposite reaction. All that means is, if we have two objects A and B, the force that A exerts on B is equal in magnitude but opposite in direction of the force that B exerts on A. So let's look at an example of that. So let's say we have a box on the floor. The box is exerting its weight on the floor, and the floor in return is pushing up on the box, and that's called a normal force. A normal force is always perpendicular to the surface. So the force is going up, so at a 90-degree angle from the surface. And these two forces are equal, and we know that because the box is not moving up, it's not going down, it's in equilibrium, it's at rest. So these forces are equal in magnitude but opposite in direction. So if we look at this, we see that the force that the box exerts on the floor is downwards, and the force that the floor exerts on the box is upwards. These are equal in magnitude but opposite in direction. So what we just talked about are action-reaction pairs, or also known as force pairs. So there are two different objects that are affected by forces. In the case we just looked at, the box and the floor were affected by the forces, and they're affected simultaneously. The box exerts a force on the floor, and the floor in return exerts a force on the box, and those two are equal in magnitude but opposite in direction. So after we know what forces are, and we know action-reaction pairs, we can start looking at free body diagrams. So in this case, we have the box again, but this time we're going to say that you're pulling it with the string. So the string force is shown as a tension force. So that's denoted by F sub T. And as always, we have the weight of the box acting downwards, which is mg, same as F sub G. And as we saw in the previous example, there is a normal force perpendicular to the surface, so there is a force going upwards, and since we're going to say the box is not moving, so the tension force has to be equal to the static frictional force. Since the box is not moving, it's static friction. If the box was moving, it would be kinetic friction instead. And always remember that it takes a lot more force to get something moving than to keep it going. So this is the formula for the friction force that's given on the AP exam formula sheet. Absolute value of frictional force is less than or equal to mu times absolute value of normal force. So now that can be broken down into a separate equation that makes it easier to see what they are. First, we have force of static friction is less than or equal to coefficient of static friction, mu sub s, times normal force. And the maximum static frictional force is equal to mu sub s times normal force. Your static frictional force will never be greater than this. It can be less than that, but it will never be greater than what this is. And the kinetic frictional force is equal to mu sub k, or the coefficient of kinetic friction, times the normal force. And mu sub s is always greater than mu sub k because, as I mentioned previously, it's harder to get something moving than to keep it moving. So let's say you're trying to push a cabinet. It's really hard to get it to start moving, but once it's moving, it's easier to keep it moving. So let's look at one where the box is on an inclined plane. So in this case, we have angle theta, and we have the box on an inclined plane. We're also going to say that the box is not moving. It's in static equilibrium. So we have the box, and its weight is going down, straight down, which is mg. And we have a static frictional force, which is acting upward on the incline because the box has a tendency to slide down the incline. As always, the normal force is perpendicular to the surface. It's very important to remember, even on inclines, the normal force is always perpendicular to the surface. The normal force is not going to be this way. It's always perpendicular. And on the AP Physics, the free response section, always draw the free body diagram without resolving it into components first, because on the AP exam, the free response section, the free body diagrams are answers. So if you resolve it into components, it changes the free body diagram, and that's not something you want to do because that might affect what score you get. Rather, if you need to redraw it, if you need to resolve it into components, you want to redraw it and then resolve it into components. So that's what I did. I redrew the diagram and I resolved it into components. So we have a normal force, and we know, as we learned in Newton's third law of motion, if we have a force going this way, we have another force that's in the opposite direction of the same magnitude. And in this case, that's mg cosine theta. And we have a static frictional force going up the ramp, so we must have something going down the ramp of the equal magnitude but opposite direction. So, and this we see is mg sine theta, and that's just a little bit of geometry, but it's easy to remember that mg sine theta is going down the ramp, and mg cosine theta is this way, because if there was no incline, sine theta would be 0, and sine of 0 is 0, so there would be no horizontal force. And as we saw in the previous problem, when the box is flat on the surface, we don't have a horizontal force. And it's also easy to remember because if we had a 90-degree angle right here, the box would just be straight up, and mg cosine theta would be mg cosine 90, which is going to give us mg times 1. And if the box was straight like this, we know that the weight would be going straight down towards the floor, and that would just be mg. So it's easy to remember that, but also in addition to the formula sheet, you are given a table of trigonometric values. That's also going to be in the description below, so you can check that out. And one last thing I want to cover before ending the video is translational equilibrium. When we have an acceleration of 0, we have mass times acceleration is equal to net force, and mass times acceleration is 0 because acceleration is 0, and anything times 0 gives us 0. So the force is 0. And as we learned in Newton's first law of motion, an object at rest with no external force will stay at rest. An object in motion will maintain a constant velocity. That means the same direction, same speed, without being affected, because there is no acceleration. And that, in a nutshell, is the dynamic topic covered on the AP Physics 1 exam. If you haven't already, subscribe to our channel and thumbs up the video. In addition to the AP exam formula sheet, there will be a link to the book that I used to prep for the AP exam. I thought it was a really helpful book. It will be in the description below. And stay tuned for more videos on the AP Physics 1 exam. Thank you so much for watching. Take care, guys.